All right. So it says, number 1, let P equal xy be a point on the graph of y equals x squared minus 8. Express the distance d from P to the origin as a function of, I should say, cut it off, as a function of x is what that should say. Does your worksheet say that?
Yeah.
Okay. So if I draw the picture of y equals x squared minus 8, it's a parabola facing upward with a vertex down at 0, -8. See, there's our parent graph, x squared, shifted down 8 units. And let's be a little more specific. Let's draw in correctly the x-intercepts. How would we find the x-intercepts of this? You could do it on your calculator with the zeros function, but how could you do it without the calculator? Plug it, okay, it involved 0. What variable is 0 when this parabola crosses through here?
Are you putting 0 for that?
Yes, okay, so we have 0, so let's do that. 0 equals x squared minus 8. So that would mean x squared equals 8, and so x equals plus or minus the square root of 8. Those are my zeros. Do you know what that is simplified in simplified radical form?
It's 2 square root 3.
Yes, 2 square root 2, yeah, 2 root 2. So somewhere in between 2 and 3, so right here and right here. So we can be a little more accurate in our drawing of a graph rather than just randomly draw those branches through the x-axis, but we're going to find the zeros. So we know the zeros to be plus or minus root 8 or 2 root 2, 0, and negative 2 root 2, 0. Okay, so we've got a picture of this thing. And now we're going to find the equation d equals something in terms of one variable, which is what we need. Before we plug it into the calculator, we need a function in terms of one variable, and then we can go find the max or min, whatever it asks for. So in general, if I were to pick any point along here, along this curve, if I called this point x, then the y-coordinate at that point would be whatever I get when I plug in x here. So we're going to just call that y-coordinate x squared minus 8. Okay? So it's x comma x squared minus 8. So if I were to plug in, say, 1, this coordinate would be 1 comma 1 squared minus 8, which is 1 comma negative 7. Okay, if I were to plug in 1. But what I want is a generic coordinate that tells me any point along that parabola. Okay? So any point along that parabola, we would call it x comma x squared minus 8. If I'm way up here, my generic point is x comma x squared minus 8. It doesn't matter. Might even be better if it's up there in the positive first quadrant. Okay? So then I'm going to connect from the origin to that point. Origin to that point, and I'm going to draw a dashed line down here, and I don't mean for it to look like it's hitting at x equals 3. I actually want that dashed line to be generic. It's hitting somewhere along the x-axis. We're going to call that coordinate x. Anywhere going with this? So I'll switch over to a different color here. We're going to label this right triangle x, and then over here, I need to erase this because I have a mess over here. I'm going to label the y-coordinate x squared minus 8. And then I'm going to label the piece that I want to write a function for d. Did you see where I'm going with this? Little right triangle trigonometry is what it is. Pythagorean theorem. Okay? That falls into right triangle trig. So according to the Pythagorean theorem, what kind of an equation do I have? It's kind of a messy one because I have x squareds under square roots. But would you agree I have d squared equals x squared plus x squared minus 8 squared? You see that using the Pythagorean theorem? No? Yeah. So Remember, Pythagorean theorem says a squared plus b squared equals c squared. That's my base equation. And what I've done here is I've called a my distance x out from the origin, and I have called b my distance x squared minus 8, whatever I get when I plug in the x, and then c I have called d. And so there's my equation, but I really want my equation to be just d equals, and so I'm going to take it one step further and say d equals the square root of that mess, x squared plus x squared minus 8 squared. So there's my equation, that's part A. Part B, I'm just asking you to plug in 1 and figure out what the distance is if x equals 1. So if x equals 1, I'm actually 7 down here. Okay, but that's not my distance, but this is the coordinate, 1 comma negative 7. So I'm asking you in part B, what is this distance from here to here, the positive distance? Okay. So you could think of it as 1 squared plus negative 7 squared. Or you could just plug in 1 to your formula. So according to the formula, what does D equal? Let's plug it in here. That's 1. Show our work here. We have 1 squared plus 1 squared minus 8 squared. So 1 squared is 1 plus 1 minus 8 is negative 7. Right over here, here it is, squared. So I have 1 squared plus negative 7 squared, which is 50. So my distance is root 50. So that's my distance. And I could find my distance from the origin to any point on this parabola using this equation. Okay. You give me the x value, I can give you the distance that we are away from it. I can also give you the y value. But it says use your calculator to graph D and then find the value of x that makes D as small as possible. That's what it should say. Makes D as small as possible. So we're minimizing this function. So we're going to take this function right here, the D equals square root of x squared plus x squared minus 8 squared, and find the minimum. So let's go ahead and do that now. So on your graphing calculator, you're going to plug in that function that we just came up with. Not D equals, but we're going to do y equals. Get second square root of x squared. Actually, I'm going to go back to I like my math type mode. So, those of you who are in classic still just have to use the parentheses. So second square root of x squared, and then it's minus, in parentheses, x squared minus 8, and then squared. That's what it looks like in math type. You're going to have to use lots of parentheses in the classic mode. So type that in, then we're going to graph it, and then we're going to find the minimum of it using our minimum function. Okay. Yeah. X squared, oh, this is plus right here. Yeah. Right. Alright, so make sure that's a plus. Good catch. Okay, does that look okay? Anybody need help typing that in? Okay, you've been on the TI-83s, are you guys okay with getting it in? You have to have double set of parentheses. It should look like this. This is our check here. If anybody did not get this, just raise your hand. I can come and look and see how you typed it in. Or have somebody next to you look at it. Okay, I'll come look at it here. Right, so we graph this thing, and then we're going to go ahead and find the minimum left bound. That's probably a good left bound there. I'm trying to find this minimum of this second one here, this valley right here. So go for right, enter, and then guess, and it's going to give me minimum is when x equals 2.738 and y equals 2.738. So that's actually not surprising. What that's telling me is that when you have a special right 45-45 right triangle is when you have the minimum distance from the origin to the point. So give a guess as to what this 2.78388822, what number that is in terms of square roots? It's 2 root 2. That is 2 root 2. So if you go back here, it says use your calculator to graph D and find the value of x that makes D as small as possible. So I was asking for the value of x, just so happens the value of y is the same. Although, okay, the value of y actually represents D. So it's not necessarily saying it's 45-45, right? Because remember, our function was not y equals, it was D equals. And so the x value that makes the distance as small as possible is x equals 2 root 2. And the actual distance, D, is equal to 2 root 2. So what that's telling me is that I am closest when I'm right straight out from it or to the left. That's what it's telling me. Because this is D equals, not y equals. That's one thing that's confusing about the graphic back here. You have no choice but to graph it y, but y isn't really y. It's D in this case. And then the next problem, y will be either A or P, area or perimeter. And then in the next one, it's going to be volume. So we're graphing x versus some other real-life dimension, okay? It's not actually the y. How would I find the y coordinate here? Well, I could look at my graph. What is the y coordinate when it's the distance is minimum? It's 0, yeah. It's 0. If I plug 2 root 2 into my formula up here, guess what I'll get? Well, I'll get 0 right here, and then 2 root 2 squared is
2 root 2 squared.
And then take the square root of it is 2 root 2, right? So that's what's happening here. So the y value is 0. Yes, the y value is 0. If I plug 2 root 2 into just the x squared minus 8 portion up here, I will get 0. So it's not a 45-45 right triangle. It's when I'm straight out to the right or to the left, right on the axis. All right. Number 2, it says a rectangle is inscribed in a circle of radius 2. So here's my radius of 2. You'll see where we're headed on this one as well, I think, pretty quickly. Let P equal xy be a vertex of the rectangle. So this could be P right here, x comma y. As a matter of fact, P could be at any one of the corners of this rectangle. But I'm going to stick to the first quadrant, okay? So P, x, y. So that means this leg is x, and this leg is y. But if I'm going to write an equation to express the area of this rectangle, I really don't want to call this y. I want to say what this is in terms of x. So let's do that first. Let's get an expression for y in terms of x. So we'll do that right off the bat. X squared plus y squared equals 2 squared. Right? The same as the one above. Can you solve that equation for y? What would it be? Maybe we'll take 2. So first of all, we're going to subtract the x squared over. So it's 4 minus x squared. And then one more step. Square root, and I'm only going to take the positive square root of it because I am in the first quadrant. So what I'm saying here is that my dimensions are x by square root of 4 minus x squared. Okay. So instead of y there, I have square root of 4 minus x squared. That's my goal, is to get an equation for the area of the rectangle all in terms of x. That's what it means to say as a function of x. And in order to do that, I had to use the Pythagorean theorem to get y in terms of x. And that's a common thing that we do when we're building functions. Because we're trying to build a function that we can then plug into the calculator or do one variable calculus on it to find the min or max. Okay? So you need some other equation to substitute in. That's what we're doing here, to get it all in terms of 1. So my area, Okay, we need to do a little more drawing on here. Of this rectangle, from here to here, if that's x, what is that length from there to there? 2x. 2x, good. And from here to here, if that length is square root of 4 minus x squared, from here to here is, so the here to here would be 2 of them, right? Is that what you said? Okay. So this is 2 square root 4, so we'll do a little squiggly here, 2 square root 4 minus x squared. Those are the dimensions of my rectangle inside of that circle. So my area formula is going to be base times height. That's the generic geometric area formula for a rectangle. And my base is 2x in this case, and my height in this case is 2 times the square root of 4 minus x squared. So that's my area formula. And we're going to find the max area that I could have for a rectangle inscribed in a circle of radius 2. We're also going to write a perimeter formula here. Perimeter is equal to twice the base plus twice the height. And so I have a slightly different equation. It's 2 times 2x plus 2 times 2 times the square root of 4 minus x squared. And we could do a little bit of simplifying if we want to, or we can just type it into our calculator just as you see it there. What would be a simplified version of area up here? We could multiply the 2's together, right? So that might be worthwhile to do. So we have y equals, clear this out, it was 4x times second square root of 4 minus x squared, right?
Wait, so what happened to the 2 in front of the square root?
That's all right. I just simplified. There's a 2 and a 2 there. I made that 4.
Oh, I thought we were doing the perimeter. My bad.
We're doing the area one here. I got it right now. So 2 times 2 is 4x. So we graph 4x times the square root of 4 minus x squared. If you want to, you can type it in before you even simplified it. Which is sometimes, if you have complicated functions, you might want to do it that way. See what happens. So we graph it. So this time we're finding the value x that gives you the max area. So what is the value x that gives us the max area for a rectangle inscribed in a circle? It's going to be this point up here, right? How do I find that point? Well, second calculate. We're going to find the maximum this time, number 4. There's a good left bound. Let's get a right bound just on the other side of where we think the max is and have a guess here. And 1.414, hey, wait a minute, 1.414, we've seen that before. What exact irrational number is 1.414? It is root 2. It is root 2, yeah. So I hope 1.414 you should recognize as root 2. It's going to show up a lot through the course. We get into trigonometry, root 2s show up a lot, and so do root 3s. So my max x equals root 2 gives a max area A equal to what? Do you remember what it was here? Remember, this formula is not really y equals, it's really A equals. And so we just found a max area of 8 square units. I didn't say what the units were. And that's when x is root 2. So when we have, basically, you get a max area, you have x is root 2, so that would be 2 root 2 by 2 root 2. So when it's a square, that's when you get the max area. What about perimeter here? X equals something gives a max or min perimeter. Let's see what it does here. We might want to draw first before we declare it. So let's see if I can remember the formula here. Going over here to y equals, I'm going to type in, I'm going to go ahead and simplify it, 4x plus 4 times the square root of 4 minus x squared. So 4x plus 4. So I'm just multiplying the 2's here. So it looks like that. 4x plus 4 times the square root of 4 minus x squared. And hit graph. Went off the screen a little bit. If I go to window, you can change your Y max, make it a little higher perhaps. Perhaps we go up to 13 and graph it again. Okay, that worked. So it looks like it is a max we're going to find here. So we can hit second, calculate, and number 4. Left bound. Let's see if I can get over here, get a right bound. And then a guess. And well, look at that. 1.414 again. Different perimeter, right? Different perimeter. 11.313 is probably can be written in radical form. But 1.414 tells me when x equals root 2 gives a max p equal to that value 11 point whatever. Here's some insight on that. If root 2 is x, then that means 2 root 2 goes from here to here. So what's another way in exact form to represent the perimeter of this square? Yeah, there's an 8 involved.
Yeah.
It's 2 root 2 times 4, or 8 root 2. That's what that number, so units, 8 root 2. And we know that, I don't think we necessarily recognize that this is 8 root 2. But if you plug root 2 into the perimeter formula, you get 8 root 2. Okay? So any questions on that? Okay, last one on here, the open box with a square base is to be made from a square piece of cardboard, 12 inches on the side. And as I said before, you're going to create this box by cutting out these squares on the sides and folding the box up. So you'll throw out those white pieces, fold it up, and create a box without a lid on it. So it says express the volume V as a function of x. Now, volume, you may not remember, but volume is actually length times width times height. It has 3 dimensions for a rectangular prism. So we've got to find the 3 dimensions, all in terms of one variable x. Okay, so here's how we go about that. This little piece from here to here, we're going to call x. It just goes from here to here. And this is also x from here to here. We're cutting out squares. So you're with me so far? Now, if I draw in all my little x's here, I can figure out the dimensions from here to here and from here to here by taking the total length of the cardboard and subtracting out the 2 x's. So if I were to cut squares that were 1 inch on each side here and here, how much of this length am I losing? 2 inches, right? If I were to cut out 2-inch squares, I'd be losing 4 inches. So, and there's only so much I can cut out. The domain is limited. How much can I cut out on x before I just don't even have a box anymore? 6. Yeah, 12 is the right, when you double 6, you get 12, and you no longer have any left. So if I cut out 6-inch square here and a 6-inch square here, I've just cut out the whole side. So you're right, so 12 will take it out. So my domain here, we should probably list our domain, is x is between 0 and 6, not including those two. So we have right here 12 minus 2x, and here is 12 minus 2x. And so my length times width times height is what? What's my length?
12 minus 2x.
12 minus 2x. My height, well, width, I should say. 12 minus 2x. And my height is going to be x. It's how much it's folded up. And I really should write down the domain, where x is an element of, or is in, the interval 0 to 6. So there's my domain in interval notation. So what is the volume if 1 inch square is cut out? Can we do that? We can do that in our heads, right? Plug in 1 for x. So we have 10 times 10, 100 times 1, so 100. 100 cubic inches. And then what is the volume if a 3-inch square is cut out? Well, plug in 3 there. And you have 6 times 6, which is 36. 36 times 3, 90 plus 18 is 108. So it gets a little better at 3, right?
Just a little bit.
Let's use our calculators to find the value of x that will make the volume larger. So you think it'll be a whole number?
Of course not.
Well, it's not 1 inch because the 3-inch one bettered that by a little bit. So the question is it going to be close to 3 inches? Well, we'll see. Let's go ahead and graph it. So go to y equals, so we have, I'm just going to type it out just as you see it there. We could actually be a little more efficient by doing this. We have 12 minus 2x. Let's go ahead and just square that, right? Times x. So we don't have to list 12 minus 2x twice. We might as well use powers, right? So we have a cubic equation. 12 minus 2x quantity squared times x. We're going to graph it. Goes way off the screen. So I might want to do it. What you can do is do a zoom and then go to zoom out, number 3. And then you have to hit enter again to actually get it to apply the zoom out. And you don't get to control the zoom out. It just does it for you. Okay, there it goes. Let's see where we're at right now. I might want to make my Y max go up to, let's just set a Y max. How about Y max 80 maybe? And then a Y scale of 10. Might want to just change our window. Y max of 80, Y scale of 10. Let's see if that'll give us a picture of where that max is. I probably should have changed the X as well. No, not quite. Think about my now. So maybe 120. So you just got to kind of play with the window. That's just the way it goes. This thing's not cooperating now. Okay, so window. My X-min, I might want to actually make my X-min be maybe something like -1. My X-max maybe be 10. And my Y-min could probably just be...
That's just what we're looking for right here.
Yeah, or what's on there? Yeah, let's go a little higher though, maybe a 120. Graph. Not quite, but that's close enough. So it looks like it's going to be 2-ish, right? Probably going to hit 2-ish. So if we go to second, calculate maximum number 4. So left bound, we know it's got to be a little bit. This is why it's good to change your X-min and X-max to something smaller, because if we had left it -40 to 40, it'd take forever to get over here to my left bound. And then right bound. There it is. And then a guess, I'll go back 1. Let's see what it ends up being. Oh, just froze. Oh. So what is yours saying?
X equals 2.
X equals 2. Good. Mine just froze. That's not right. And when x equals 2, what does it tell you the volume is over there?
128.
128? Okay, so when x equals 2? So what does that tell us in the context of the problem? So it says, for what value of x is the volume the largest? What size squares should you cut out? And 2-inch squares, yep, if you want to maximize the volume. Okay. So if you're doing some packaging or something, you want to maximize the volume, 2-inch squares, that's the secret for this particular size box. Now you can change this up and make it not a square. Okay, a lot of box lids are rectangular, not square. And then that would change the problem up. Okay. So, any questions on that?